I'm going to be going over how to create a sampling circuit on Simulink. First, we're going to have our message signal that we're sampling, which is going to be the sine wave. And then we're going to use a rectangular pulse train to sample that signal. For the sine wave, left click 2 times, and then we're going to change this to sample base. We're going to have the amplitude as 1 by 0. We're going to use 1000 samples per period, 0 offset samples, and we'll set the sample time to 0.001 second or 1 millisecond. And then for the pulse generator, we're also going to do sample based. We're leaving the amplitude as 1. The period is going to be 100. And then pulse width we can vary. For now we'll do half the period, which is 50. No phase delay, and sample time we need to set it the same as the sine wave, which is 1 millisecond. Let's also drag out a scope and a spectrum analyzer. So now let's connect the sine wave and the pulse generator to the scope and the spectrum analyzer. For the sine wave, the sampling time is 0.001 seconds or 1 millisecond. So there's 1 millisecond per one sample, and there are 1000 samples in one period. So that means each period is 1 second, and the frequency of the message signal is 1 over the period, which is 1 Hertz. For the pulse generator, each sample is 1 millisecond long, and there are 100 samples in one period. So that means each period is 0.1 seconds long. The sampling frequency is 1 over that period, which is 1 over 0.1 seconds, which is 10 Hertz. And the duty cycle is the pulse width over the period, which is 50 over 100, or 50%. If we run the simulation, you'll see that yellow represents the sine wave. If we zoom in, we'll see that we're supposed to get one spike on each side of the spectrum, since this is a double-sided spectrum. And the blue is the pulse generator spectrum, and this is in the format of a sync shape. And then if we take a look at the scope, we can click view and change the layout into 2 down, so we can separate it. And then we can use the zoom feature to look at 3 periods. And you can also put a cursor on. And these are the plots that we should get. And then to sample the sine wave with the pulse train, we're going to use a product block. Its inputs are going to be the sine wave and the pulse generator, and this multiplies both of these. So if we connect this to the scope, we hit run again, and we're going to change the layout again, and we'll zoom in on a couple cycles. We'll see that the sine wave multiplied by this rectangular pulse train gives us this plot. So the rectangular pulse can either be 1 or 0. When it is 1, it multiplies and copies this segment of the sine wave, as you can see right here, and when it's 0, it doesn't. And this is what it looks like when it's sampled by the rectangular pulse train at 50% duty cycle. And then we can change the duty cycle to 25%, and then this is what we would get. We can reconstruct the original sine wave by using a low-pass filter. We're going to change filter type to IIR, and then the passband edge frequency and the stopband edge frequency we can view by hitting view filter response. So the sine wave's frequency is 1 Hertz, so we want to shift this region over to the left more. I'm going to set the passband at 200 Hertz and the stopband at 1000 Hertz. And if you hit apply and view filter response, we can see that the filter's cutoff frequency, which is where it is -3 decibels, it's going to be between 100 and 500 Hertz. And then we're going to put this into the scope, and I'm going to use another spectrum analyzer. So if we hit run, we're going to change the view again, This bottom plot is the reconstruction of the sampled waveform. The amplitude has decreased, but the period and the frequency is just about the same. And if we look at the spectrum analyzer, all of this is noise. It is less than -75 decibel milliwatts. So if we zoom in on this part, let's bring out the peak table, we just about get around 1 Hz, which is the frequency we started with. By the Nyquist-Shannon sampling theorem, the reconstruction is possible because the sampling frequency is at least twice of the message's frequency. In this case, our sampling frequency is 10 Hz, which is 10 times that of the message's frequency of 1 Hz. So let's see what happens when the sampling frequency is less than twice of the message's frequency. We'll keep the sampling frequency at 10 Hz, and we'll increase the sine wave frequency to 8 Hz. If we decrease the samples per period to 125, with a sine wave having 125 samples per period, each of its period is now 0.125 seconds, or 125 milliseconds. That means the frequency of the sine wave is now 8 Hz. And for proper reconstruction, the sampling frequency needs to be twice that, which is 16 Hz. With the sampling frequency still at 10 Hz, which is less than what we need, let's see what we get. So as you can see, when we attempt to reconstruct the sine wave, we have a frequency that is less than the original frequency. This is known as aliasing. And this is basically how you make the sampling circuit on Simulink.